Hello everyone, myself Prabhashri, Assistant Professor of Mathematics Department. Today we are going to see about a case study video in Mathematics.
Good morning everyone, this is Shahana from First BME. Today I am here to give an introduction to the physical concept called application of the residual theorem in finding electric fields around a cylindrical conductor. So today I am gonna present a case study which connects complex mathematics with real world physics. We will explore how this powerful advanced mathematical idea, that is the residual theorem, can be calculated to the electrical field around the metallic cylinder. So let's begin with the physical setup. Imagine a very long straight metallic cylinder like wire. Let's say it is electrically charged. When this happens, the space around it is filled with electric field, and it is invisible, but it get influenced by the nearby charges. So the intensity and the direction of the field depends upon how far you are from the surface of the cylinder. Usually, these how to finding the electric field around the cylinder or any other conductor, it is done by mainly in 3D objects. It is done by the physical rule called Gauss law, which is one of the most basic laws in the physics. But what if the given setup for you is very complex, which has multiple wires, or it has what complex shapes, or it has various or varying boundaries? So what are the possibilities or what are the requirements on these conditions? How will you find when these are the difficulties or these are the complex structures that is implemented to a conductor? So what can be done? That's where our advanced mathematical tool called the residual theorem comes in, which is came to just simplify all these complex processes and we always get correct answers from this residual theorem. So then it is followed by the other parts of the case study video, and let's explore and dive more concepts and more applications and how it's useful in our real life. We will get be known. Thank you.
The computation of integrals with infinite limits or discontinuous using semicircular contours. Conformal mapping used in engineering and physics to transform complex shapes into simpler ones, helpful in solving boundary value problems.
Analytic continuation helps extend the domain of complex functions beyond their initial region of convergence. Control theory using stability analysis of systems using methods like plots and Laplace transforms.
How residue theorem applies to a cylindrical conductor. Now let's look at how this applies to our case of a cylindrical conductor. When a cylinder is charged, it creates an electric field all around it. This field is strongest near the cylinder and becomes weaker as you move farther away. The pattern is radial and symmetrical, meaning the field lines spread outwards evenly in all directions. To find the exact strength of this field at any point, we need to calculate how the electric potential changes in space. And instead of solving this using traditional vector methods, we can represent the potential using a complex function which, as I said earlier, is well behaved almost everywhere except at the center of the cylinder. This center point acts as a singularity, and the electric field around it can be studied by applying the residual theorem to that point. By doing this, we don't have to study every possible path around the cylinder. Instead, we study how the function behaves near that one important point and then gives us the answer to the whole circular region. In the end, this approach confirms that electric field decreases as you move farther from the cylinder and points outward, just like what we expect from classical physics. The power of residue theorem is that it simplifies the process and allows us to solve complex field problems more elegantly.
mathematics, physics, and engineering. Studies fluid flow and wave functions involving engineering complex. Study fluid flow and aerodynamics using conformal mapping, quantum mechanisms, and wave functions involving complex valued intervals.
Real world applications and conclusion. So, why this is important in real life? The residue theorem is not just a mathematical curiosity, it has real applications in fields like electrical engineering, where we design systems with multiple wires and conductors, telecommunication, where field calculations are important for cable shielding, and medical imaging technologies like MRI, where electromagnetic fields play a key role. Thank you.